All right, it's recording now. Now, I was talking before, well, we covered simple systems like spring mass and spring mass dampers and spring mass damper systems. We saw how can we find the equation of motion, and we solved those equations of motions. We got the system response, different properties of the system we defined. For a system with a damper, we defined a couple of things. System without damper, like a spring mass or a pendulum, we defined the natural frequency time period. For a spring mass damper, we defined damping ratio, damp natural frequency. We needed those parameters, critical damping, to describe the system. Now, what I want to do today is more like a little bit of a turn before we continue going that direction. We're going to have a couple of sessions today. Probably next week, we will talk about a few things about these systems, right? Related to these systems before we move on. Now, first thing I want to talk about is the way we derive the equation of motion. Remember, the equation of motion was that second order differential equation that we solved for our systems, right? Spring mass and a spring mass damper or pendulum. Now, we were always using Newton's method, right? We were drawing free body diagram and then kinetic diagram, and we were putting things together, and we could find the equation of motion. Now, that's not the only way to do this, right? Newton's method is the most familiar method to us. We've been using this in engineering, mechanical engineering, since I would say junior year, or when you started looking into statics. When you took that course, you became familiar with Newton's laws. Maybe you were even familiar from high school, some of you, with these Newton's laws. So we're using those, we've been using those, but there is another way to find the equation of motion, and that way is using the energy of the system. So no need to look into free body diagram, different forces. What we care about is the energy of the system, right? Different types of energy, different forces that are contributing to the system's energy and how they are changing. And using those, and only those, we can actually find the equation of motion. So that's what I'm going to take a look at. Now, it's up to you which one you prefer. There are some systems that if you use energy method, it makes your life much easier. But I would never tell you that I want you to find the equation of motion for this system using energy method. It's up to you to use whether to use Newton's method, going from free body diagram, kinetic diagram, or use energy method. But I want you to be familiar with this method, because in more advanced systems, it can be a lot easier to just look at the energy instead of going through the whole free body diagram and drawing forces. So I'll put this under energy method. Energy method. I can say, let me see if I have a bit of wording there. It's an alternative. That's a good way of saying this. Alternative approach to Newton's method. So you don't have to deal with free body diagrams and the whole dilemma related to that. And second thing you can put on is it focuses on systems energy. And the way it changes. Now the systems we have seen, it was either a spring mass / pendulum or a spring mass damper, right? We've seen pretty much two types of systems, and those two types are representatives of pretty much a broad range of systems we're going to deal with in mechanical engineering, right? We have been dealing with. You're in your last year, so you've dealt with so many systems already. Now, I'm going to be a little more structured, right? And we call them conservative and non-conservative systems. And we look at how could energy method be used for a conservative system and how could it be used for non-conservative system. Now, a conservative system is pretty much a system that all the forces are conservative. Well, it doesn't really say that much, right? What I'm trying to say is that, well, let's phrase it this way. A conservative force, the work it does on the system is independent from the path you take. Now, this is still a little unclear. A good example of that is if you think about the work done by gravity. If you're taking stairs going up 2 floors in a building versus taking the elevator and going 2 floors up, and you go 2 floors up. Now, it doesn't matter which path you take, taking the stairs or the elevator, as long as the height is the same, the amount you go up is the same, the work done by gravity is mg delta h, right? The change in height. So it's independent from the path you take. This is a conservative force. So if we have a system that the only force applied to it is gravity, that is a conservative system, because all the forces applied to the system are conservative forces. Now, we don't get into details about conservative, non-conservative. I just want you to get a sense of why do we call a system conservative system and why do we call a system non-conservative system. But almost all the forces we deal with are conservative forces, except the forces that are taking energy from the system, if you want to think about it that way. When the system is leaking, quote unquote, energy, that's a non-conservative system. So you can think about friction as a non-conservative force because it depends on the path, right? How far you go, right? Friction, the amount of energy is taken out from the system changes. Damping, the one we already know, is a conservative, non-conservative force. So sorry, I'm not sure if I said friction is non-conservative. Friction also is non-conservative force. Damping is non-conservative force. You will see that we actually model friction as a damping. So as I said, any system has 3 elements. One that stores energy, one that stores kinetic energy, one that stores potential energy, and one that dissipates the energy. The one that dissipates energy typically is a non-conservative force. So for a conservative force, it's generally in energy method, let me put it this way. What we say is that the sum, actually this is under conservative force. So conservative system. For a conservative system, think about conservation of energy. It's a very good example. The energy, or let's put it this way, the sum of kinetic energy and potential energy. Let me see what they put there. Yeah, just the same thing. Remains constant. It's pretty much all you need to know about these systems. What I'm trying to say that if I represent kinetic energy with T and potential energy with U, this is a constant value. This is representative of kinetic energy of the system. And this is the representative of potential energy. Now, if I take derivative with respect to time, well, the right side is constant. So derivative of that with respect to time, right, it doesn't change over time, becomes 0. This gives me this. T plus U, d dt, T plus U is equal to 0. And this is what you need, all you need to find the equation of motion for a system. As long as you can find the expression for kinetic energy for a system and the expression for potential energy for a system, you can find the equation of motion. So from here, let me see if I can I don't know, we can write this. We use this to find a equation of motion for the system. So as long as your system is conservative, meaning that there is no energy leakage in that system, no damping, no friction, no nothing like that, you can use this. Now, what happens if we have damping? Right? We've seen systems with damping. So how can we use energy method to find the equation of motion for those systems? Now, for non-conservative systems, all you got to do is you have to add the work done on the system by that non-conservative force to this equation. So what is that work? In this case, we're just dealing with viscous dampers. So I'll just write the expression for the non-conservative system with a viscous damper. Right? It's the specific kind of system we deal with. So in this case, this becomes ddt, well, this side is still the same. But now the right side is not going to be constant, before you take derivative. The right side is the work done by damper. So I'll represent that with W, work done by non-conservative force, which is damper, from point 1 to point 2. Right? The system moves, it depends on the path. So from point 1 to point 2, how do you get there from point 1 to point 2? The work done, and it's done by damper, so I use C representative as a viscous damper. Now, because this is a work, let me just write the expression before taking derivative. Then I'll take a derivative with respect to time. So we have it as T plus U is equal to work done by damper, 1 to 2. This is bad. And since this is a work that takes energy out of the system, I put a negative here. So that makes the mathematical expression, I would say, correct. Now I'll take derivative with respect to time again. Same thing. T plus U. This gives me minus d dt W 1 to 2. I have to put 2 here for damper. That's all you need. The only difference is that the right side is not 0 anymore. Now actually you have an expression you have to calculate. Now what is this W from 1 to 2 work done by damper? You can show this. Let me make sure that I put everything there. Yeah. You can show that as is the integral from x1 to x2. Right? The system is moving. Think about wherever you are at the beginning and wherever you are at the end. It depends on the path, so we have to take that into account. Force, it's the work. So force times displacement. Right? In integral form, Cx dot, right? The force of a damper, viscous damper, is Cx dot. And the displacement, dx. That's all you need. So you have to find this integral, which might look a little scary, but you will see how we actually get away and go around it and find a way not to take this integral. That's what we do all the time when we're dealing with systems with viscous damper. But this is a general expression. So work from 1 to 2, work done by damper, is from x1 to x2 Cx dot dx. Now, sometimes I take this negative minus from this equation and put it here. So you can also write it this way. Keep this positive and put a negative here. Doesn't matter. Right? As long as that negative is taken into account, you're good. Okay, so before I start looking into a couple of examples, we have to establish what are these T and U. Like damper we know, so C, damping coefficient, we know x dot is the velocity of the system. We have to somehow find the result of that integral. But what are T and U? What are kinetic energy and potential energy? Let's just be more organized and put them in categories. Right? So I'll put sources for kinetic energy. So we know exactly what we have to look for when we're looking at a specific system to use energy method. Now, what are those sources? Let's put it here. So the first source of kinetic energy, can someone actually tell me, do you have anything in mind about this source of kinetic energy from what you know from dynamics and physics? What could be a source for kinetic energy in a system? Think about the spring mass damper or a pendulum. What do you think is going to be the source for kinetic energy or contributes to the system's kinetic energy? Okay. You know, the most familiar equation for kinetic energy is 1/2 mv squared, right? You've seen that. So mass of the system is the main source contributing to the system's kinetic energy. What I'm going to do is that I'm going to separate this mass contributing to kinetic energy into two classes or categories. A type of mass that is a moving mass, translational mass, and the type of mass that is a rotational mass. Spring mass damper, the mass there, and the mass in a pendulum. Just to make it easier, depending on what type of system we are dealing with. So the first one, let's put it as translational mass. And the kinetic energy for that, if I show that with TR, would be 1/2 mv squared, which I just presented that by mx dot squared, x dot squared. All right, you've seen this before. So it's old body of yours, hopefully from physics. You've seen it. Now the second one, still mass, but I'll say rotational mass. All right, if you just have a pendulum fixed some ceiling, it's not translating, it's rotating around a fixed point. I should have used probably TT for this. Makes more sense. This is T translational, T rotational. That would be 1/2I. Right, now we deal with mass moment of inertia for that system. The mass has around that whatever point is rotating around. And omega squared, which I represented with theta dot squared. Right? Omega is derivative of rotational displacement with respect to time. And the last case, let's say when we have both. You might see it when we have a pendulum and a cart later on, maybe when we talk about, if we get a chance to talk about Lagrange method in systems in multi-degree freedom, you'll see that. But a system can be rotating and translating. You've seen that in dynamics. So in that case, you have to take both into account. So rotation plus, I'll put it this way, translation. T, kinetic energy, is just basically T translation plus T rotation. Nothing really new, just sum them up. These are all the sources for kinetic energy you're going to deal with. When you're given a system, start looking for these. Do I have a mass that is translating? So that's one source of kinetic energy. Do I have a mass that is rotating? So another source. Both of them are happening, so I have to take into account both these to make sure that I'm accurately or correctly finding the kinetic energy for the system, that T parameter in energy method formula. Now, sources for kinetic, for potential energy. Can someone mention something familiar, something that contributes to potential energy? There are three there too. Although we're not going to talk about the third one, but, or we don't use it. But.
Gravity.
Gravity, right? Exactly. So let's start with gravity. And if I represent that with UG as potential energy from gravity, would be just pretty much mg delta h, right? The familiar form. If you put it mgh, just remember that h is the change in height. What else? Something that we've
spring.
Spring, exactly. Spring. So source for kinetic potential energy is a spring. And what is the kinetic, potential energy for a spring? You've seen that too from hopefully before. But it's 1/2 kx squared. Or you can go with s squared, as long as you know that whatever you're finding is squared should be the amount the spring is stretched, or compressed. If I stretch the spring, obviously I'm storing energy in it. If I'm compressing it, I'm storing energy in it, because when you let it go, it suddenly expands. The last one that we don't really talk about, is buoyancy. Now, buoyancy is also a source for potential energy. If you think about it, a good example of it would be when you put a piece of wood on water surface, in water. When you try to push it down, what happens? If you push it down, you are actually, or better to say, the potential energy is being stored in that piece of wood because of buoyancy force. So when you let it go, we've all seen that. Any floating object, not just a piece of wood, it starts going up and down, right? Because the potential energy that was stored in that floating object turns into kinetic energy when you let it go. So it creates an oscillation. You have an object floating on the surface, going up and down, up and down. So that's the buoyancy in that case, which is the source for your potential energy. I don't think we're going to talk about any system with buoyancy, but you probably can see examples in vibrations textbooks. I don't know if there is any in our textbook, but in other textbooks you can find. Okay, now we are ready to look at a couple of examples, right? We looked at energy method. We said whether a system is conservative or non-conservative. Where these are the general expression you have to form, or equations you have to form to find the equation of motion for the system, depending on if you have a damper or you don't, or any non-conservative force. And we said these are the sources for kinetic energy and potential energy. So when you form T and U for equation, keep these in mind. So let's start with something that we already know, something very familiar. Right? So let's see how does this work for something that is not that complicated. Right? Let's start with the spring mass system. Let's say I have a mass, then I have a spring there with the stiffness K. And the question is, find the equation of motion for this system if the oscillation starts from equilibrium point. If the oscillation starts from equilibrium point. So let's see what we get. We have to get the same equation of motion, all right? See how it works. What is the source for potential energy here? From all the sources I mentioned. I don't know why my U is so ugly.
The spring.
We have the spring, all right?
And gravity.
And, well, is gravity doing any work? That's the question.
Well, no, not in this case.
So there you go. We can just safely ignore gravity. So what is doing the work? Because there is no delta H, right? So it's 0. Is 1 over 2 kx squared. That's all we have for potential energy. How about the kinetic energy? What do we have here?
Translational mass.
We have translational mass. Thank you, Dominic. 1 over 2 mx dot squared. All right, now we have everything we need. We know U, we know T. There is no damping there, right? So W1 to 2 for damping is 0. I don't have any non-conservative force. In this case, in our case, it's just damping. So let's figure out how can we find this now. How can we go from this, what we know, T and U, to equation of motion? So this tells me that I have to take derivative with respect to time from 1 over 2 kx squared plus 1 over 2 m x dot squared is equal to 0. How do I do this? Now let's just separate them. Let's do this. I actually should. This is a better way of doing it. I'm just setting up my colors, so don't worry. Let's take a look at the first term, this one first, and then look at these two. So d dt 1 over 2 kx squared. The rest is just math, has nothing to do with vibrations. Now I have to take derivative with respect to time from a function or an expression. Well, 1 over 2k is just constant, it comes out, from x squared. Now x by itself is a function of time, so I'm taking derivative of a function that itself is a function of time, and it's a square. All right, I'm doing this, 1 over 2k dt x squared. Now since x is a function of time, right, it's much easier if I just use chain law or chain rule. Right? 1 over 2k d dt, I can say I'm taking derivative as d dx x squared times dx dt. Right? I said, well, instead of taking derivative with respect to time from x squared, I'll just say, I'll use chain rule. I'll say d of something dt can be d of that thing dx times dx dt. This dx dt is x dot. d dx x squared, well, it becomes 2x. So 2x comes out, cancels 1 over 2. This becomes k x x dot. I'll do the second one. d dt 1 over 2 m x dot squared. Follow the same process. 1 over 2 m, just constant. I take it out. Now d dt, now I have x dot squared. My process is still the same. Right? I use chain rule. I would say d dx dot x dot squared times dx dot dt. Right? Instead of taking derivative with respect to time of velocity, which is the function of time, I just use a chain rule. Now dx dot dt becomes x double dot. Right? x dot is squared, derivative with respect to x dot, well, it becomes 2x dot. 2 comes out, cancels out 1 over 2. This becomes m x dot x double dot. These are the two derivatives I needed to form the main equation. Now let's see what we got there. So if I put everything together, d dt, I can do better. T plus u is equal to, well, I just put these things together. It becomes m x double dot plus kx, and I take x dot out. I just factor it out because they both have x dot is equal to 0. Now I have this expression equal to 0. I am interested in when this becomes 0, right? If x dot is 0, this expression is always 0. X dot is multiplied by that parenthesis, whatever is inside that parenthesis. So that's not what I'm looking for. I don't care about when everything is 0. Nothing is happening. So forget about x dot equal to 0. This is velocity is 0, nothing is happening. The system is standing still. So the other part is 0. I make that equal to 0. mx double dot plus kx is equal to 0. And here you go. You have your equation of motion. This is what we got from Newton's method. Equation of motion. It should be the same. Equation of motion of the system is the same. Okay, so any question about this, guys? So we formed potential function, or we found the potential energy, found the kinetic energy for a system, and we took derivative, right? The derivative part is just math. It doesn't even have anything to do with physics, right? You see there is no free body diagram, no concern about forces, the direction is correct or not. As long as you take all the energy sources into account, you are good. Right. So let's take it one step further, and let's take a look at a system with a damper. Let's do that. Example. Now what I have is spring mass damper system. Make it better. This is K, this is C, and this is M. These are supposed to be on the ground. They're not flying. I guess you know that, but okay. Just showing that there is no friction. So the same problem statement. Find the equation of motion. Find the equation of motion for this system, you know, assuming that the motion starts from equilibrium point. Now, well, kinetic energy is still the same, 1 over 2 kx squared, as long as x, well, the motion starts from equilibrium, so x is the amount of deformation. We are taking x from the equilibrium point, right? Either this way or the other, it doesn't matter. Kinetic energy is 1 over 2 m x dot squared, because we only have translational mass. That's pretty much it. Now we have a damper here. The only difference from what we had before is a damper. Let's see how can we deal with that scary integral. 1 over 2 c, let me just keep negative here. x1 to x2, cx dot dx. We can put 0 to x because motion starts from x equals to 0, ends at some x. Now, let me use, well, this we already found. d dt t plus u, I'll just keep it here. Let me just use what we got from before. We got m x double dot x dot plus k x dot. This is the left side of the equation. because what we are trying to form is we're trying to form this, right? We're trying to form d dt t plus u is equal to minus integral from x1 to x2 c x dot dx. That's the general expression you want to form to get the equation of motion. Now, so let's take a look at the work done with damper. 1 to 2, C. Now, what do I do here? I have to find this derivative. Right? Let me actually write it in a better way. Now, I have to find this derivative, d dt integral, keep negative here. Oh, x1 is 0, x2 some x, cx dot dx. Now I have to take derivative with respect to time from an integral taken over x. Right? This is dt, but the integral is over x, right? Along the path. It's the main reason, because the non-conservative force, it depends on the path that it takes. So let's do a trick. Instead of figuring out how to do this integral, what I know is that derivative of an integral over derivative of time, well, let's put it this way. Let me form that sentence correctly. We have an integral, right? What I want to do is I want to get rid of this integral. How do I do it? I'm looking at that and I'm seeing the derivative with respect to time and then the integral over x. So what if I can convert that integral to an integral over time instead of over x? Then I can say, well, derivative with respect to time of an integral over time, well, becomes whatever is under that integral. So what I'm trying to say is that let's somehow find a way to convert that dx into dt inside that integral. How do I do it? I again use the chain rule. I say dx, right? Let me make sure that I said everything I wanted to say. Yeah. Dx, I can rewrite this as dx dt times dt. It's a small mathematical trick. Dx dt is x dot, so this becomes x dot dt. Right? This is the key to how do I deal with that integral. Now, since I'm changing the integral, let me write it first. So d dt, this becomes minus integral c, well, instead of dx, I put x dot dt, so this becomes x dot squared dt. Now I have to look at the limits for the integral. Since I went from x to t, limits also are going to change. Instead of 0 to x, now I have 0 to t. Right? And the time that I get to position x instead of position x. Now is much easier. I'm taking derivative with respect to time, and I have an integral over time. So in your mind, you can think about it this way, that this dt here and this dt here take care of each other. So all is left is minus cx dot squared. Beautiful, right? Didn't have to deal with the complication of the integral, just did some change in the variable, and as easy as that, I could get what the result of the integral is. Now I can use this and form the equation. So the left side is mx double dot plus, this becomes mx double dot, if I didn't make any mistake, plus kx x dot is equal to minus cx dot squared. The left side, the right side, just put things together. Here, I'll just move things around and take x dot out again, plus Cx dot plus Kx times x dot is equal to 0. And as before, I don't care about when x dot becomes 0, because then there is no motion in the system. I get nothing out of that. So the first part is equal to 0, and that is the equation of motion. There is. This is what we got from Newton's method. No free body diagram. Again, most of it is mainly math. As long as you can identify the sources of energy in the system, you're good.
Professor, could you explain why you're taking x dot out from the last step until you get the equation of motion?
Well, so I get, if I put everything together, eventually it becomes this, right? It becomes mx double dot x dot plus cx dot squared plus kx x dot is equal to 0, right? Now I said I have to find where this becomes 0. Or I can just factor out x dot. All of them have x dot. Then I get to this equation there. I don't know why I draw a line at the top. I get to this equation there. Now, looking at this equation, I'm solving a mathematical equation. I want to know, when does this become 0? Now, when x dot is 0, this is always 0, because x dot, think about, you have two expressions, a, b is equal to 0. Right? If b is 0, well, this is always 0. So you get nothing out of it. So out of this, I get two things, if you think about it. I get this, and I get x dot is equal to 0. I have two things multiplied equal to 0. Either of those two things can be 0. X dot equal to 0 gives me nothing. It's a trivial solution, if you want to think about it in terms of math. It's a trivial solution, because x dot is equal to 0 means the system is not moving at all. So nothing is happening. But the other one, when I make it equal to 0, that is the equation of motion I get. I don't know if it makes sense.
Thank you. Yes.
Okay. So it's all into it. Right? It's easy as that. The trick is to get the sources for energy right, and to get the result of that integral right. Let's take a look at an example that's a little more unfamiliar. We haven't seen this, and we haven't used Newton's method to solve this. Let's say I want to draw, the problem is I have a disk like this. It's rolling on the ground. There's no friction. Now this disk is connected to a wall by a spring. It's oscillating, right? It goes back and forth because of the spring. So it's K. Disk has the mass of m and the radius of r. We want to find the equation of motion for this when it oscillates like this, goes back and forth, like rolls around and goes back and forth. What is the equation of motion for this? So find the equation of motion for small oscillations. You'll see why. And for a disk I, or mass moment of inertia, if I call this point O, the center of the disk, is 1/2 mr squared. Hopefully you know that from dynamics. When you have a disk rotating around its center, the mass moment of inertia is 1/2 mr squared. Now, let's see what we got there. So, what is the source for potential energy here? Or sources?
The spring.
We have the spring. 1 over 2 kx squared. And we're going to take this as the equilibrium point. I didn't put it here, but the motion starts from equilibrium. So 1 over 2 kx squared. Is there anything else for potential energy?
No.
No. Dominic is on fire. Take a look at kinetic energy. What are the sources for kinetic energy?
We have translational and rotational.
We have translational and rotational. Exactly. Hopefully everyone can see that. So when I have a disk rotating, right, if you think about it, this moves in this direction along a straight line. So there is a translation there, right, going back and forth. But this translation comes with a rotation. Right? The disk is rotating and translating. So we have both sources of kinetic energy. Again, if it was just a cart or a box, it only had translation, right, back and forth. Right now, it translates, go back and forth. At the same time, to be able to translate, it also rotates. So it has both translation and rotation. So I put both of them, 1 over 2 mx dot squared. For rotation, I will take, let me see if I can erase this part. I will take rotation, let's do it this way, theta. So this becomes 1 over 2 I O theta dot squared. It rotates around the center O, theta amount. And we said oscillation is small, so that theta is a very small angle. It goes very small around its equilibrium point. Now here is the problem we have now. We have two expressions written in x. One is written in terms of theta or theta dot. How do I deal with that? This is only we'll talk about degrees of freedom, but this is a kind of system that I should be able to describe its motion using only one variable or one coordinate system. But right now I have two. I have x and theta. So I have to be a little bit smart and find out a way to write one of them using the other, or find the relationship between r and theta, which is not that difficult to find. If you look at this disk here, I'm going to draw it here again. Now this is point O, almost in the center. If this is theta, let's say we have a point there, it rotates and gets here. Original position, some position later on during the motion. So this is theta. Right? And this length is r. Now look at this. This is x. Right? Now for small theta, right, look at if this point is very close to this point. Right? I have a triangle like this. If I can draw it correctly. So there's a triangle is here. Point O is there. This is theta. This is r. This is x. So x is equal to r sine theta. Right? Hopefully you see that in this right triangle there. This is a triangle I got from here. Just looking closely at the triangle. Now, again, all the way back to probably first or second, I think the first class we had, we said whenever we said small oscillations, right, small rotation, meaning that we can go with the assumption that we make to linearize a system. What was that assumption, or what were those assumptions? Can someone tell me?
Sine theta equals theta and cosine theta equals 1.
Exactly. Thank you, Chris. It would be R, so this becomes almost equal to R theta. So now we have X and theta written one in terms of the other. If X is equal to R theta, well, X dot is R theta dot. R is fixed, just take derivative with respect to time from both sides, you get theta dot. So now what I can do is that I can write, let me write everything as a function of, what did I do there? Let me do the same thing I did before. You can either write everything in function of theta or X. I guess because two things are functions of X and one is theta, it makes more sense to write that one expression as function of theta, rewrite that as a function of X. So I'll write it this way, m x dot squared plus 1 over 2 I-O. Theta dot is x dot over r squared. Now everything is in terms of x. Right? We took advantage of the fact that this is the small oscillation. So let's do what we do. Well, and there is no damping there, right? So work done by damper is 0. Or non-conservative force work is 0. There is no non-conservative force. If we had friction, that would have been the whole new story. So d dt, the rest is math, right? T plus u is equal to 0. This means that d dt of 1 over kx squared plus 1 over 2 mx dot squared plus 1 over 2 I-O x dot over r squared. If you take derivative, right, let's just start from the first one. We did that before. We did that before. We know that this becomes d dt 1 over 2 kx squared. We know this becomes x. Well, I have to remember to keep k there. So this becomes k x x dot. The second term, we also did that, d dt 1 over 2 m x dot squared, right, from before. This becomes m x dot x double dot. The third term, relatively new. Let's see what happens there. It's not really new, it's the same process. 1 over 2 I-O x dot over r. Let's put it this way, squared. We can write it as d dx x dot. Right? I'm following the same process I followed before when I was taking derivative of 1 over 2 m x dot squared. Right? This becomes 1 over 2 I-O x dot squared over r squared times dx dot dt. Dx dot dt is x double dot. Take derivative with respect to x dot from this. Well, x dot squared becomes 2x dot. So 2 and 1 over 2 cancels that. They cancel each other out. This becomes I-O x dot over r squared times x double dot. So this is the first expression. This is the derivative with respect to from the second expression. This is the derivative with respect to from the third expression. Let me make it less crowded here. All right. Now I have everything. I just put them all back together. All right, these three, I need everything. I have everything I need. My goal was to form this is equal to 0. And I just put everything together. So it would be m x double dot x dot plus I-O. Let me write it in a way that is easier to separate things. I-O r squared x double dot x dot plus k x x dot is equal to 0. And hopefully by now you know where am I going, right? I take derivative, I take x dot out. I try to fit it here. Hopefully one can see that. mx double dot plus IOR squared x double dot plus kx multiplied by x dot is equal to 0. So I just took x dot out. I forgot that actually everyone can see it because it's not a board anymore. I'm not blocking anything, or you are not blocking each other's views. Old habits die hard. Doesn't matter what I write. So we have this, right? Obviously, I don't care about when x dot is equal to 0 because then there is no motion. I care about what is happening inside this parentheses, and I make that equal to 0. And I can even factor out x double dot from the first two expressions. So that becomes m plus IO r squared x double dot plus kx is equal to 0. And here is my equation of motion. And this is what we had before, right? This is the equivalent of mass, and we already have k. So you can, all these equations of motion, when we find the rest is what we already know from before. We know mass, we know stiffness, we can find natural frequency, we can find system response as long as we have the values we need, system characteristics and initial conditions, and go on. We can go a little further, and since we know IO is equal to 1 over 2 mr squared, let's simplify this. So this becomes m plus 1 over 2 mr squared times 1 over r squared, right? I wish I would have written everything together, but plus kx is equal to 0. So this is simple, can be even more simple. R squared and R squared, they cancel out. So it becomes 3m over 2, if I didn't make any mistake. X double dot plus kx is equal to 0. Let me know if you see something went wrong somewhere. This is even a simpler equation of motion because I'm given the radius of the disk and the mass of the disk. So I can actually find the mass moment of inertia. Hopefully I got the same thing I got from before. Yeah. And you can find natural frequency obviously from here by just dividing k over m equivalent. Right? If I tell you what natural frequency is, would be k over 3m over 2 would be 2k over 3m. I'm just saying. The rest is the same also if we can find system response and everything. So now that was an example that was much easier to solve using this. I encourage you to go home and try to solve this using Newton's method. The good thing about energy method is that you don't have to be worried about all those greedy needy about whether whether you take care of the right direction, positive, negative, your free body diagram is right. As long as you take care of the energy sources in the system, the rest is just math. Now, it depends on how comfortable you are with math and taking derivative. It's relatively straightforward if you ask me because it's just taking derivative. So it's up to you which method you choose to use to find the equation of motion. Once you find the equation of motion, the rest is straightforward. We already found everything we wanted in terms of theory of vibrations. Now I'm going to do another example. We'll see how far we can go in that. That's something that you've seen also. This example. Let's see how can we solve this using energy method. If you remember, I gave you this and I actually gave you the solution in the lecture notes. I told you to go think about it and then I put the solutions in the same set of slides. Now I had a spring here, hopefully it's familiar. This is K. It's rotating around the point O. This is L over 4. This is 3L over 4. And we have a damper here. Anything else I'm missing? So this is the mass of this is M. Find equation of motion for small oscillations about point O. Let's call this point O here. Now, I don't know if you looked at or tried that problem, right? I'm hoping that you did, since I asked you to do it. Let's take a look and see what we have here and how can we deal with this system. See how far we can go. If we can't finish it, I'll just post the solution. And this is C. This is damping C. So we have kinetic energy and potential energy. What are the sources for these? What is the source for kinetic energy here? Should be very comfortable with this by now. You've seen multiple things. You know, source of kinetic energy can either be a rotational or translational mass or both. Which one do we have here?
Do we have both because it rotates and then we have the spring?
Well, you just have to look at the mass. Don't care about the rest of the system. Does your mass translate or rotate? Or it does both? That's the only thing you need to care about. Now, you have a bar, it's rotating around point O. It's not going anywhere. There is no translation. So the only thing you have is just the rotation. I'll call theta double dot, assuming that this angle, let's say we have some rotation, a small rotation, this angle is theta. That's pretty much it. What do we have for, let me call this A and call this B on the rod from the equilibrium. Just keep in mind this motion starts from equilibrium. So the potential energy would be 1/2 K, and how much K, or the spring is, if the motion is clockwise, how much that spring is compressed? Well, we put it as XB squared. Now, we already have two variables, theta and X. Right? Before I even move to damping, I have to figure out how can I get rid of one of them. Because again, this is the type of system that I should be able to describe its motion using one variable. We are going to take a look at the geometry. This is the rod, the bar. This is point O. I have theta here. This is XB. And this is 3L/4. This one is L/4, and this is XA. This is also theta. So what is XB? Or can someone tell me the relationship between XB and theta now? Come on, folks. Take a look at this triangle here. This one there. What is the relationship between XB and theta? It's a right triangle.
Sine theta is XB/3L/4.
Exactly. So sine theta, thank you, is equal to XB/3L/4. So XB is 3L/4 sine theta. And we're talking about the small oscillations, so 3L/4 theta. So I can write this as 1/2 K 3L/4 squared. Let me just put everything. No, it's better. Squared theta squared. Right? I write this. Now I have two things. Both of these sources are functions, are written as a function of theta. Now let's find derivative. D dt t plus u. That would be d dt 1 over 2 I-O theta double dot plus 1 over 2 k 3L over 4 squared theta squared. This should be d. Now, I'll just write this, but you do the same thing you did before. D dt becomes d d theta dot or d theta times d theta dt. For theta dot, expression with theta dot, d theta dot, d dt becomes d theta dot times d theta dot dt, which becomes theta double dot. So if I do this calculation, this expression gives me I-O theta dot theta double dot, and the other one gives me k 3L over 4 squared theta dot. This is what I got for this part. Right? This is what I'm looking for. d dt t plus u is equal to w from 1 to 2 c. Sorry, d dt of that, derivative of that expression. d dt w from 1 to 2 c. So I got the left side of the expression already. How about the right side? The right side is the work done by damper. So I'll start from w from 1 to 2 c. Or I can just write everything. Why not? This is d dt minus integral from x1 to x2 c. Now this x dot is the amount the damper, the velocity at the point the damper is. So that's x dot a. Keep in mind, this is point A we're talking about, the left side of the bar. And that's where the linear velocity of the damper is. And this would be d also xa. Take a look at it, see if it makes sense. It's a general equation we had for damper. But now instead of x, we have xa because we care about where the damper is connected. The same story about where the spring is connected. Now I want to do the same thing I did before, but it's a little more tricky here. Let me separate these points so things are not mixed up. What I want to do is that, well, I have to find a way to get rid of this x dxa, and I want to convert it into dt like I did before. Right? Hopefully it makes sense what I'm trying to say here. You were following before, hopefully that you're following still. So I'm going to write it the same way. I use a different color so it's not mixed up. dxa can be written as dxa dt times dt, meaning that it becomes x dot a dt. So I can plug it here. d dt minus integral, well, this becomes 0 to t, was 0 to x, x1 is 0, x2 is x, some position that we are. I change the variable into integral from dx to dt, so it becomes 0 to t, c x dot a squared dt. So what I get out of this, well, the derivative with respect to time from an integral over time, it just comes out as cxa dot squared. And this is the left-hand side of the equation. This is the right-hand side of the equation, like this equation there. So the only problem left is that, well, I wrote everything based on theta, right? I got this one for the left-hand side is based on theta. Now for the right-hand side, I got this, which is based on x. XA or X dot A. So I have to go back to the geometry again and write this XA as a function of theta, which is pretty straightforward. Right? If you look at this side now, this triangle on this side, and this is still theta, so you can actually write XA, right? The same story you did for previous one. Sine theta is equal to XA over L over 4. So XA is L over 4 sine theta. For linear system, L over 4 theta, or linear motion. Now we are looking for X dot, so we just take derivative from both sides. If XA is equal to L over 4 theta, X dot A is L over 4 theta dot. This is squared, so I'll do it this way. So now I have the left-hand side as function of theta and theta double dot, and I have the right-hand side as function of theta double dot. So I started from the integral. I did what I did before. I changed derivative. I changed the variable in the integral from dx to dt to get rid of the integral and get whatever is under that integral. What came out was a function of x. So I used geometry again. I said this system should be described with one variable and wrote x as theta. Now I have everything I need. I can just put these things together. If you do that, hopefully I did it. You have the left-hand side, you have the right-hand side. I'll just give you the final answer. If you do it, you will get IO theta double dot plus 9L squared over 16K theta plus CL squared over 16 theta dot multiplied by theta is equal to 0. So here is your equation of motion. Right, we don't care, sorry, this is theta dot. You don't care when theta dot becomes 0. We care about the first part, right, plus CL squared over 16 theta dot plus 9 L squared over 16 K theta is equal to 0. Now this becomes your equivalent of mass, this becomes your equivalent of damping, and this becomes your equivalent of stiffness. And the whole thing, oops, that's not what I wanted. The whole thing is the equation of motion. Equation of motion. That's it. Take a look at this example again. This is a very important and useful example. It's very similar to what I posted for the last example for a spring mass system. I just wanted to solve this, and you see that you get the same equation of motion as the one you got from by using Newton's method. Okay? End of the class, folks. Any question?